Thanks for the introduction. My name is Cory. I'm a student from the Technion, and today I will be presenting the one-pass compactor. It is joint work together with Professor Erez Petrank, and it is an intellectual abstract as we propose a new algorithm, but we do not accompany it with implementation nor evaluation. So the one-pass compactor is a full heap compaction algorithm. It requires a single heap pass, which is nice because traditionally the complexity of compaction algorithm is measured by the amount of heap passes that are necessary for it. And it is parallelizable, which means that it can be suitable for multicore platforms. The motivation for this research is pretty clear. Garbage collection is very common in modern environments, and many garbage collection methods cause fragmentation. This fragmentation hurts program performance, first by making the allocation process more difficult or even blocking it when there is enough free space in the heap. And second, by making the usage of for resources such as the cache and virtual memory inefficient. Luckily, we can solve this problem by compaction. So when we think about compaction, there are really two goals. The first and the obvious one is to compact the objects in the heap, meaning gathering all live objects together into a contiguous space. But the second one, just as important, is to keep the correctness of the program by updating each pointer to point at the new location of the object it refers to. So it's easy to think that if we have an object that moved, we need to fix the pointer to it, or else it might be catastrophic for the correctness of our program. In this paper, we focus on mark compact, in which compaction is following a marking phase. This approach enjoys low memory overhead, and it preserves object order, which has been proved in practice to be beneficial for program behavior. So a problem that we encounter is that full heap compaction requires high time overhead. And throughout the years, there have been many ways in which we can deal with it. The first one is reducing the complexity of the compaction algorithms. Naturally, if there is less work to do, this work is done faster. Additionally, the compaction can be made incremental, meaning that instead of compacting the whole heap at once, we divide the heap into different segments, and at each point, we only compact a segment. This not only shortens the wait time, but it can also increase throughput, as a segment should only be compacted if it is necessary. Additionally, we can make the compaction parallel, in which case multiple threads will run the compaction algorithm together, thus the overall time will decrease. And the compaction can also be made concurrent, in which case compacting thread runs in parallel with a user application, and there is no wait time, or very little. So all of these approaches are widely covered in literature. This is just a short list. In this work, we focus on, first and foremost, reducing the complexity, and then we also offer a parallel version of the algorithm that we present. So we begin with asking the questions, how many heap passes are necessary for mark compact? Now, in the worst case, a single pass at least seems unavoidable. Imagine a case in which there is a little bit of free space in the beginning of the heap, and then a lot of objects scattered throughout it. We will need to go into each one of these objects and copy it into the beginning addresses. Previously, in the past, compactors required 3 heap passes. An example for that is the Lisp2 compactor, which in the first heap pass installed forwarding information inside of objects. Then in the second pass, it used this information to fix pointers. And in the third pass, it actually moved the objects. Later, there have been compactors that only required 2. We will delve into some of them later in this presentation. Examples for that is the Yonkers threaded algorithm and IBM's compactor. And eventually came the compressor, which only required 1.x heap passes, with 1.x meaning one pass over the whole heap, and then another pass, which is a pre-processing traversal of an auxiliary data structure, which is smaller than the heap, but proportional to it in size. And a follow-up question that we ask is, can one pass be reached? And as the name of this paper might hint, we answer with yes. In this paper, we present the one-pass compactor. It is the first compaction algorithm to only require a single pass. And later, we extend it and offer a parallel version of it. So during this presentation, we will begin by reviewing existing algorithms that serve as the building blocks of the one-pass compactor. We will go through the threaded algorithm of Yonkers and through the address mapping approach showcased in IBM's compactor by Abu Ayad. We will then notice beneficial properties of this algorithm, and we will combine them together to create the one-pass compactor. And we will finish by discussing a little bit about the parallel extension, since we do not have time to cover the whole thing. So in the threaded algorithm, the idea is to take pointers to an object and transform them into a linked list beginning in that object's header. Then when this object is handled and a new address for it is computed, we can traverse this linked list and fix all pointers in it. It can be done in a smart way, which does not require extra space and instead uses existing fields. So a short example of this process is if we have, say, objects A and B, which contain a pointer to object C. When we reach object A, we notice the pointer in it, and we add it to the threaded list going from C. Then we do the same to object B when we reach it, and we reach a state in which all objects are threaded into, all pointers to C are threaded into a linked list beginning in its header. Then when we reach object C and we calculate a new address for it, we can traverse this list and update the pointers in it to reach the final state in which the pointers are fixed. So we make a distinction between two kinds of pointer based in the direction in space to which they point. If a pointer comes from a higher address to a lower one, we call it a backwards pointer. And symmetrically, if it goes from a lower address to a higher one, we call it a forwards pointer. And we will use this definition to notice beneficial properties. So an observation that Yonkers makes is that when the heap is traversed sequentially, and whenever a pointer is reached, it is threaded to the object it points to, then when we reach an object, all forwards pointers to it have already been threaded, which means that we can use this threading mechanism to fix all forwards pointers during the first heap pass. This observation helps Yonkers create his algorithm that requires only 2 heap passes. In the first pass, we traverse objects by order, and whenever we reach an object, we start by updating all pointers in its incoming pointers threaded list. Then we thread all pointers outgoing from it, and then in the second pass, whenever we reach an object, we update again all the pointers that have been added to his threaded list since the previous pass, and we move the object. It's important to notice that this is a sequential algorithm, and not only it is sequential, it is notoriously hard to make parallel, as it really builds on the order in which the traversal is done. The second building block of the compactor is IBM's, of the one-pass compactor is IBM's compactor by Abu Ayad. This compactor uses an auxiliary address mapping, which is kept in a compressed way to not require too large of memory overhead. And we basically can think of it in the following way. It gives us the functionality to give it as an input the old address of an object, and get as an output its new address. This can be used to compact the heap in 2 passes. In the first pass, whenever we reach an object, we move it to its new location, and then we calculate and record its mapping in the auxiliary map. And then during the second pass, we fix every pointer we reached based on this address mapping. So we make this following observation that so far has been overlooked. If we have a sequential heap traversal, and whenever we reach an object, we record its old to new address mapping, it means that every object, whenever we reach an object, we already have this address mapping for every object before it. And this can be useful because we can use mapping to fix backwards pointers on the first heap pass. So a corollary of these two observations is that we can combine these methods and fix all pointers in the first heap pass, since we have a mechanism to fix forwards pointers and a mechanism to fix backwards ones. And this leads us to the one-pass compactor in its sequential form. The algorithm is quite simple. What we need to do is to traverse the heap in order, and then for every object we reach, we start by calculating its old to new address mapping and record it. Then we update all pointers that have been threaded to it. We move it to its new location. And for each pointer in it, based on the direction into which this pointer points, we fix it with the relevant method, which is either threading for a forwards pointer or address mapping for backwards pointer. So this algorithm only requires a single heap pass, and it incurs the same space overhead as a Boyad's compactor, as it uses the same mapping mechanism. And we will now see a short example of it. We have objects A, B, and C, blue, red, and green, respectively. We begin by reaching object A and calculating and recording its old to new mapping. Then, since there are no pointers threaded to it yet, we move it to its new location, and we fix pointers in it based on the relevant method, in which case it's a forwards pointer, so we thread it to the pointed object. Then we reach object B. Again, we record its old to new mapping. It does not have any pointers threaded to it, so we move it to its new location, and we fix the pointers in it based on the relevant approach, in which case, since it is a backwards pointer, we fix it using the address mapping. Last, we reach object C. Again, record its old to new mapping. In this time, we do have pointers threaded to it. So we traverse the threaded list and fix these pointers. And then we move it to its new location and again fix pointers in it. This time, again, a backwards pointer, so it is fixed with mapping. And this was it for the sequential algorithm. In the sequential case, objects are traversed by their order in the heap, which helps us have certain guarantees about them. We know that based on the direction that a pointer points to in space, what is the useful way to fix it. But when we want to think of the parallel case, which is important since many modern systems have multiple cores, if not all of them, we cannot rely on these spatial considerations anymore. So we need to employ a paradigm shift. And instead, we want to think about temporal properties. Basically, we would like to replace the spatial notions of forwards and backwards with the temporal notions of not yet and already. We would like to simplistically say that we will use threading to fix pointers to objects not yet visited and use mapping to fix pointers to objects already visited. Sadly, life is not simple. When we have a parallel compaction algorithm running on multiple threads, objects can be visited concurrently, and different threads advance in different speeds, so we need to take all that into account. As you all know, the devil is in the details, and we will not have time in this presentation to focus on everything we do to make the algorithm parallel. So instead, we will discuss a few key points of this parallelization journey. First of all, as mentioned, we have this paradigm shift of making the consideration temporal instead of spatial. Then we take the critical section of the threading operation, and we make it contain only a single compare and swap instruction. We have to make sure that when a pointer is threaded to an object, it will actually be fixed when that object is handled. We need to make sure that when we move objects, we do not break any linked list, as this can hurt the correctness of the program. If not careful, we can run into an ABA problem, so we have to avoid that as well. And not only we need to keep the program correct, we also need to do so in a manner that will allow us to compact in high quality and achieve satisfying load balancing between the threads running the compaction algorithm. So to conclude, in this paper, we present the one-pass compactor. It is the first compaction algorithm to achieve heap compaction using only a single heap pass. And it achieves that by combining beneficial properties of existing algorithms. And eventually, we also provide a parallel version for that algorithm. So thank you for listening. If you have any questions.
Thank you. This was a great talk. Do you have plans to implement it?
I'm not sure yet. I'm still doing my undergraduate studies, so obviously I did not have time so far. Hopefully in the future.
Maybe I can convince you and Erez to implement it in V8, because I think this could be really useful in the browser context.
Okay.
We'll talk later.
Other questions? It's sort of a related question, which was, so this has the best asymptotic performance, but do you have a sense for, like, what would be your guess for what algorithm would perform best?
So this is a great question, as we know that the threading operation in the general case can be less efficient than the address mapping approach due to cache behavior. We like to think about this measure of pointer locality, which will measure the average distance that a pointer points to. And our hypothesis is that if a program exhibits a high pointer locality, then the threading method will be more efficient, and it could be very competitive to, say, the compressor.
So at the risk of showing my ignorance, I'm not in this area, but so is it necessary to move every object in the heap? Because if the heap, let's say the object takes, say, 4 kilobytes, and I'm allocating things in terms of 4 kilobytes, why should I move it?
Oh, so again, great question.
It looks like you could be doing less than one pass.
Yeah, that's a good question. Again, this is a theoretical work, and in many systems that are actually implemented, big objects are not moved.
Thanks a lot.
Thank you.